Hi, this is Gert Kootstra. Welcome to my presentation. I'm here among some of my plants, as you can see, and you probably recognize immediately that those are plants. But for an automatic system, this is not that straightforward because of the variation in the appearance of these plants. And that's a topic that I would like to discuss with you today. So, agricultural robotics and the challenge of variation. Why robots in the first place in agriculture? Well, they can help us out to make agriculture more sustainable. They're an enabling technology for precision agriculture, for ecological farming. They can help to improve the resource efficiency, reduce pollution, waste, improve breeding, solve the labor scarcity issues, reduce the cost and improve the quality of the produce. So they're an important tool in a sustainable future of agriculture. But there are challenges in agricultural robotics. We defined a few. The first one is the variation. What I just started out with. Products look different. There's incomplete information. Sensors might not provide us the information that we need. There might be occlusions, like in the picture here. And there's the issue of safety. How can a robot deal in a safe way with the produce so that it's not damaged or harmed? Today I will focus on the challenge of variation. So in the field, we can have different types of variations. So it's different plant species, different cultivars, different growth stages. The soil composition might be different. Illumination might be sunny or cloudy. There might be moisture on the field. The weather differences are there, seasonal differences. But also, for instance, differences on the camera type and the camera position used to acquire data. Now, deep learning methods we've seen in the past years can deal with variation and appearance in illumination actually quite well. However, what we see is that these methods do not generalize completely to other fields and cultivars. So I'll give you an example of a use case where we detect plants in different fields. So here we have a study with 22 different fields, data from these fields, images from these fields, with different cultivars of sugar beets and volunteer potato, with different soil composition and different growth stages. We used for the detection of the plants a standard YOLO V3 network to detect both the crop plants but also the weed plants. And then we studied the effect of variation in the training set. What we did here is that we used data from different training sets, going from 5 different training sets to 20 different training sets. Where every training set comes from a different field. That's increasing the amount of variation. Note that we kept the number of training images the same in all cases. It's always 500 images. So here we have 100 images of 5 different fields. Here we have 25 images of 20 different fields. And what you can see here clearly in the graphs, that by improving the variation in the data set, we're improving the performance. We can of course also look at the effect of the training size, so the number of samples in the training set. That's what we did here. Now we use the data from all the 20 different training sets, and you can also again clearly see that the performance is increasing when we increase the number of training images. And that's true for the sugar beets and also for the potato plants. Now, basically what this shows us that if we have an additional set like this with some training samples, and here we have the full distribution of our crop and weeds, we can see that we have only a limited, we cover only a limited part of the distribution. Now we can add more samples. That would mean that we get here larger blobs that we cover quite well. We can also add more variation. So we cover a large part of the distribution, but still there are holes in between. And then if we do both, we hopefully can get to methods that generalize very well to unseen situations in different fields in the future. So that's where we need to move into. Now, one way to help us doing that is something that's called active learning. So in this study, we developed a method that help the system to choose training samples that are most valuable when the robot encounters new situations that it cannot handle yet. This requires that the system becomes aware of such situations so that it can actually select training data that's useful. What we use here is mask RCNN, but it's been modified in the mask head and also in the box head by having dropout there. Well, dropout, many of you might use it during training, but here we use it during inference. That means that if we pass the network through, by random, some of the neurons are dropped out. They don't contribute to the final results. We get a result. We do this several times. The dropouts are random, so we get slightly different results every time. Now, by comparing the results of the different runs, we can get to a level of certainty of the network. The assumption here is that if the results are very similar, the network is quite certain about this data, and if not, then it's very uncertain. Now, we do this based on the certainty on the mask, on the classification, and also of the presence of the object itself. Now, we use this in an active learning context. So we have an initial training data set, and then we have a pool of unlabeled images. What we do is that we train the model based on the initial training data set. That model is then applied to the unlabeled images. We select the unlabeled images that the network is most uncertain about. That becomes a new set. We take a human annotator to annotate that data. We add the data to the training set, and then we go to the next cycle. Again, we train the model. We use the model on the unlabeled images. We select the most uncertain images, or the images that the network is most uncertain about, and again, add that, and we continue that process. Now, we applied that to the detection of broccoli and different defects on broccoli. So this is a classification problem. And what you see here is a comparison of using a random sampling strategy, where we increase the number of training samples step by step in steps of 200. And you see that also when we randomly select new data, we are improving the performance. And that makes sense. But if you use the active learning method, you see that the increase in performance is much steeper. So we actually really select images that are helpful for the network to train and to capture the variation in our data set. The black line here is the training performance that we get using all the 14,000 images in our training set. So you see that already after 2,500 images, the active learning method gets pretty close to what we can achieve with 14,000 images. So this is very helpful. Now, to wrap up this presentation, there is variation, which is a big challenge and hampers agri-food robotics. There's a need for methods that generalize well to the new circumstances. Now, deep learning can deal with some of this variation, but there are often still new situations that are outside of the training distribution that we cannot deal with. Now, we can collect more data, of course. We can do this randomly, but the active learning methods can help us to pick out the most valuable training samples to improve the performance. I'd like to thank you for your attention. Again, my name is Gert Kootstra. If you want to contact me, here's my email address, and the QR code provides information about my LinkedIn profile. During the presentation, you've seen some other QR codes. Those give you access to the papers if you want to read more on the details of these studies. Thank you.